All right, so now we're going to talk about root finding methods. And before I do that, let me sort of just briefly survey some class of problems. Uh, so, so a mathematical problem is that of solving algebraic equations. And there's sort of four cases, if you will, some of which are easy and some of which are more complicated. And we'll develop methods for each of these in turn, except for the first one. So the simplest case you could have is obviously the scalar linear case, right, which is that ax is equal to b, where ax and b are scalars. And so you know that x is equal to b over a if a is not equal to 0. All right, so that's not very exciting. So let's look at the case of sort of scalar equations, but nonlinear. So we want to have f of x is equal to 0. All right, so this is one of the things which we'll focus on, at least initially. And then another important class are sort of systems of equations which are linear. And this is really sort of what is called numerical linear algebra. A large part of numerical linear algebra is about efficiently solving large systems of linear equations. And that's when you have, say, a matrix A, a vector x, and a vector b, and you're trying to solve for x. Right? And then the fourth case is if you have systems of equations, but they're nonlinear. Okay, so you have a vector valued function f, which depends on the vector x, and this gives you a vector of zeros. Okay, so we're going to look specifically at root finding first in the case of scalar nonlinear equations. Okay, and again, the problem is that if you're given a function f of x, right, I want to find a point, let's say alpha, such that f of alpha equals to 0. Okay, so most of the methods which we'll study are what are called iterative methods. So most methods are iterative. Which basically means that they generate a sequence which converges to the root. Okay. All right, so we're going to start this problem of root finding for scalar nonlinear equations by considering what are called simple enclosure methods. And simple enclosure methods are informed by this observation coming from the intermediate value theorem that if a function changes sign over an interval, then there is at least one root in that interval. Okay, so let me just remind you of the intermediate value theorem. Which we had discussed before. So if f is continuous in the interval from a to b, and k is any number between f at a and f at b, then there exists a point C, which is in this open interval from A to B, such that f at C is equal to k. Okay, So an immediate consequence of this is a result which is going to be then used to construct or to justify, it's like the bisection method. And that's a corollary of this theorem, okay, which says that if f is continuous, again on this interval, and f at a times f at b is less than 0, which basically means that f changes sign. You know, that the function values at a and b have different signs. That means that 0 is between fa and fb, and so by the intermediate value theorem, there has to be some point in this interval between a and b where f at that point is 0. Okay? Then there exists c in the interval from a and b such that f at c is equal to 0. Okay? So let's look at an example of how one might apply this, right? So if you want to prove that some function f of x, say this polynomial f of x is equal to x cubed plus x squared minus 3x minus 3, okay? You want to prove that this has a root in the interval from 0 to 2, right? So all I have to do is I have to evaluate f at 0 and f at 2 and show that they have different signs. Okay, so f at 0 is just 0 plus 0 minus 3 times 0, minus 3 is minus 3. F at 2 is 2 to the third power is 8. 8 plus 4 minus 3 times 2 minus 3, so it's 8 plus 4, it's 12, minus 6 is 6, minus 3 is 3. Okay, so f at 0 is minus 3, f at 2 is 3. So by the intermediate value theorem, there exists a root somewhere in the interval from 0 to 2 where f at that point is 0. So by IVT, there exists some alpha in the interval from 0 to 2 such that f alpha is 0. Okay, all right. So now we're ready to sort of look at what is called the bisection method. Okay, so the bisection method is as follows. So we use the midpoint of the interval use the midpoint of the interval a to b, right, as an approximation of the root. Okay, and then if that is not good enough, that approximation is not good enough for whatever reason, we use the initial value theorem, intermediate value theorem to find which half, so which subinterval So there's two possible subintervals, in which has the midpoint as one of them. So a to a plus b over 2, or a plus b over 2 to b, right, which contains the root. And repeat. Right? So the idea, of course, is that you start with an interval a to b such that the function value at a and the function value at b is different. Okay? Sorry, the sign of the function value at a is different from the sign of the function value at b. Okay? So you can then evaluate the function at the midpoint a plus b over 2 So it has some sort of well-defined sign, positive and negative, or it could be 0. And if it's 0, then you're done, right? You should just stop there. You found a root, but in most cases, it's not the root, in which case it has a definite sign. And then because a and b have different signs, either the interval a to a plus b over 2 or the interval a plus b over 2 to b will be such that the function value changes sign. It's like over that subinterval. Okay, so one of them will have that property. And then you can sort of repeat the process now with this smaller interval instead. Okay, so that's the basic idea behind the bisection method. So let's work through a few steps of this just so that you get a sense as to what is going on. So let's look at the example we had before, which is f of x equals to x cubed plus x squared minus 3x minus 3. We knew that f at 0 is equal to minus 3 and f at 2 is equal to 3, right? So the first iteration is I is equal to 1, so alpha 1 is equal to the midpoint of the interval from 0 to 2, so that's 1/2, it's like 0 plus 2, which is 1. Okay, so that's my first approximation of the root. I can evaluate f at that midpoint. So you can check that that is 2 minus 3 minus 3. So that's 2 minus 6, which is minus 4. Okay. So now I have to pick the interval either 0 to 1 or 1 to 2 such that the function value changes sign. So it's easy to check that the interval from 0 to 2, from 1 to 2 is what you're looking for. So by intermediate value theorem, right, a root, right, must lie in the interval from 1 to 2. Okay, so let's look at the I equals to 2 case. Alpha 2 is now the midpoint of the interval 1 to 2. So that's 3 over 2. I can evaluate f at 3 over 2. That's going to be minus 15 over 8. I can look at the interval from 1 to 3 over 2 or 3 over 2 to 2 and figure out which one the function changes sign over, right? So you really want the interval from 3 over 2 to 2. So by IVT, the intermediate value theorem, a root must lie in the interval from 3 over 2 to 2, because f at 3 over 2 is negative, f at 2 is positive, so this is the interval where the root is guaranteed to be in. Okay, so we can do this one more time. I equals to 3, alpha 3 is equal to 1/2 3 over 2 plus 2, which is 7 over 4, and then f at 7 over 4 is 9 over 64. All right, that's positive. You want to find the value. You want to find the endpoint which has a negative value, right? So 3 over 2 is a negative. So again, by intermediate value theorem, a root must lie in the interval from 3 over 2 to 7 over 4. Okay, all right. So let's just keep going. So I equals to 4, alpha 4 is the midpoint of this interval, which is 3 over 2 plus 7 over 4, the whole thing divided by 2. So that is 13 over 8, which is about 1.625. And then the actual root is 1.732. Okay, so the point is that you can get closer and closer, arbitrarily close, it's like to this, through this process of successive bisection. Okay, all right. So hopefully that gives you an idea of how the algorithm is set up, and then the next thing we'll do in a little bit is to analyze the rate of convergence of the bisection method, and then state the algorithm in pseudocode. All right, so I'll stop here for now.